So I'm going to discuss actually sort of a story about inverse scattering. So I'll start with a scattering phenomena in the context of scattering by bounded inhomogeneities that are bounded support. And then I'll connect this scattering phenomena, which is non-scattering, to some non-self-adjoint eigenvalue problem. And then I'll tell you actually how this special eigenvalues can potentially be used to get information about the material properties of the inhomogeneity. So here it's a visual display of scattering theory. So basically, so there is a background, and you probe that area, say in this square, by an incoming wave. Mathematically, that incoming wave would be the solution of the background governing equation. But somewhere in this area that we probe, there is a perturbation of compact support. And then this incoming wave, in this case, the first row, it's a plane wave, is disturbed by this inhomogeneity. And then say after it goes through this perturbed background, then one has both the incoming wave and the so-called the scattered wave. So here I display both, and here is the scattered wave. So this is basically the forward scattering. One could possibly send point sources, as in the second row, and the same phenomena happens. So the direct scattering problem consists of actually solving PDE, elliptic PDE in the frequency domain, as I displayed here, or hyperbolic PDE in the time domain in the entire space. Okay, the data comes in identical way. Now, the inverse scattering basically starts with information, the scattered field, but of course the scattered field not everywhere is known. So say one actually measure the scattered field far from the perturbation, and with that information and having this information for sufficiently for sufficient probing waves, one would like to actually recover the perturbation. So one could recover everything, could recover the support, or maybe some information about the perturbation actually that affected this incident wave. So basically, this tells the story of direct and inverse scattering theory. So in my talk, I'm going to briefly discuss, try to understand the scattering phenomena in the context of scattering theory that would lead me to these eigenvalues, to these special frequencies. So my discussion will be in the frequency domain. All right, so most of the time, one actually has a response of the inhomogeneity to the probing wave, okay? And that's why it's possible to solve the inverse scattering problem. There are situations when, so if you probe, say, with a lot of plane waves, say, theoretically from all possible direction, it is possible to superimpose those plane waves, for example, in such a way that there is no response from the perturbation, from the inhomogeneity, okay? So this is the fundamental sort of question that I'm going to analyze and eventually use to solve the inverse problem, right? So more broadly, can we find a physical incident wave such that if you probe the given inhomogeneity with that incident wave, you don't get any scattered field, any response from this perturbation? So in some ways, later you'll see we are going to image by non-scattering, okay? All right, so the outline of my talk is the following. Basically, I mentioned, so the title describes the whole story that I'm going to talk today, but I'm going to start, as I said, with non-scattering phenomena and connect it to this special transmission eigenvalue problem. So they both are, so to speak, the cornerstone of this superposition idea, which leads to non-scattering. No response from the inhomogeneity. Then I'll briefly discuss the state of the art of the transmission eigenvalue problem. I'll tell you what is really the fundamental connection between this non-self-adjoint eigenvalue problem and non-scattering wave numbers, non-scattering phenomena. And mathematically, there is where non-self-adjoint spectral theory meets the so-called free boundary regularity. And then I'll tell you how these eigenvalues can be measured from the scattering data and extend this idea to probably bring in new eigenvalue problems and use the eigenvalues to solve the inverse scattering. So this is actually a direction that have been developed for many years. So I'll present results from many people. But my collaborators list for parts of the work I'm going to present includes Lorenzo Audibert, David Colton, Hussein Madar, Peter Monk, Michael Fogelius, Jingyi Shou, and Yangguan Zhang. Okay, so now I'm going to give the mathematical formulation of the slides I showed for the scattering phenomena. So in general, as I said, we may have perturbations that are disconnected. So support is disconnected. And in general, I'll assume that the boundary is Lipschitz. This is the default sort of assumption. And the scattering discussion will be in the context of elliptic formulation, so frequency domain. And for, say, in acoustic scattering, I'll call the wave number k the frequency that is scaled by the sound speed in the background. So for sake of simplicity, my background will be homogeneous. The sound speed k, I mean the k will be exactly that wave number corresponding to that homogeneous background. So now in the perturbation region, I'm going to assume that the perturbation is potentially anisotropic. This would include not only acoustic, this would include, say, like Maxwell's equation, electromagnetic for especially polarized incident fields. But the concept that I'm going to discuss is much more general than just the equations that I'm putting on the slides here. So one could discuss this concept in the context of elastic scattering or the 3D vectorial Maxwell's equation. All right, so the coefficient of the perturbation of the constitutive parameters of the perturbation will be a matrix valued function A and a scalar function N, which in general can be L infinity. Later on, I may require more regularity. And A and N are one outside the support of perturbation. Okay, so what I'm going to assume, I'm not going to go into when this problem is well posed. I'm going to assume that the coefficient and the smoothness of the boundary, that it's Lipschitz, are such that the scattering problem is well posed. Okay, so so here the incident field comes in here. So theoretically, you may send a wave that actually solves the equation of the background everywhere, possibly without a sort of manifold of the zero measure. Okay, so it's like a surface or a point source, or maybe an entire solution to the Helmholtz equation. In particular, if we actually send a plane wave, the incident field has this simple form, then one has the total field and the corresponding scattered field, right? So you see that the total field inside the inhomogeneity satisfies this equation, and outside the inhomogeneity is going to satisfy the Helmholtz equation, because actually it's included in here because A and N are identity and one respectively outside the perturbation. All right, so now the incident field, the scattered field, of course, it's going to depend on the direction of propagation of the plane wave, as well as the wave number of the plane wave, right? So it is known in scattering theory that if you look far away from inhomogeneity, the waves are going to look as spherical waves, and so the first term in the far field asymptotics looks like this, and this function, depending on the angular of the observation and angular of the incidence, and of course the incident, the wave number, but as a function itself, it's a function of the angular observation, is called the far field pattern. In scattering theory, knowing the far field pattern or knowing the scattered field up to the perturbation of the inhomogeneity is the same thing. And this is basically what the famous lemma tells us. All right. So as I said, the fundamental question of all my discussion is, suppose that you probe the area where you expect to be a perturbation by several plane waves in all kinds of directions, right? So theoretically, for all possible directions. So basically, you get some thing like, and then you measure the far field, the corresponding far field. The far field is a complex valued function. Say for one particular direction, you get something, one of the columns, and for all directions, you are going to get something like this, right? So one axis is the incident direction, and the other axis is the observation direction. So you get this far field pattern, right? So now the question is it possible to superimpose these far field patterns in such a way that scattered field is zero, right? So first, in this statement, we have the superposition part. What does it mean to superimpose the far field pattern? Superimposing the far field pattern, it means that we integrate sort of as it's a weighted superposition. So we integrate the far field pattern against an L2 function. And this is actually this famous sort of far field operator or relative scattering operator, or known as the S matrix, right? So this is an operator from L2 on the unit sphere or circle, depending on the dimension, to L2. Okay, and it's captured this superposition concept. Now, the model that I'm discussing here is linear. So the governing equation and everything is linear. So the linearity tells me that the superposition of the plane waves is of the far field pattern is actually the far field pattern of the scattered field if actually I send the superposition the same with the same density G of the plane wave, right? So in other words, if I send this VG as an incident field, which is a physical incident field, then I get as a far field, I get this F evaluated at G. So this function is known as the Herlotz wave function. All right, so you have this object, the far field operator or relative scattering operator, and actually this is not sort of new object. This has been studied and is fundamental to scattering theory. In particular, for years, people have studied the scattering poles, resonances. It's a beautiful area of scattering theory with amazing results, and many of you have contributed to this area. Another way of there are many ways of defining the scattering poles, but in the context of this object, this relative scattering operator, the scattering poles are the poles of meromorphic extension as a function of k of the scattering operator. So there is a vast literature on the scattering poles. As I said, many of you have done work in this area. I'm just putting this book by Dadlov Usursky on the mathematics of resonances. So now my point is now, actually, I'm not going to discuss here the scattering poles. Rather, I'll introduce this concept of non-scattering transmission eigenvalues. But this concept I'm interested in also stem by kind of very fundamental properties of this scattering operator, relative scattering operator, because it's incoming to outgoing. Which makes the operator compact, actually. So I would like to, instead of looking at those poles of meromorphic extension of this operator, I would like to look at the values of k for which this operator is not injective. So injectivity of this far field or relative scattering operator leads to non-scattering phenomena and transmission eigenvalues. Okay, so in particular, I'm going to look for G's, for densities such that fkg is equal to 0. That makes the relative scattering operator non-injective, okay? So basically, this is exactly what I posed at the beginning. So is it possible to superimpose? So is it possible to find a Vg, that produces 0 scattered field, or equivalently far field? So fkg is equal to 0. So this has been an area that started actually with the work by Kirsch and Colton Monk in 1986. And there is a vast literature in this field, especially after 2010, when people showed actually the potential existence of such non-scattering phenomena. In fact, actually, before 2010, a lot of work was done in the context of spherically symmetric media, where you are going to see actually that you have a perfect sort of non-scattering for particular wave numbers. Anyway, a lot of literature, not exclusive, but a comprehensive list of references we put in this monograph with Colton and Hadar, CBMS. Actually, it started thanks to Professor Atkinson, who actually organized a CBMS NSF conference in Arlington. It was a wonderful experience. And as a result of that conference, actually, we wrote this monograph. And because of the development in this area, we decided actually to write a second edition where we have actually added like half of the original monograph, so it contains more a sort of up-to-date results. Okay, so so let me try now to figure out mathematically how to find those wave numbers for which we have this non-scattering superposition of plane waves, right? So it is easy, instead of looking at the equation for the total field, we look at the equation for the scattered field, and the equation for the scattered field becomes this one. On the right-hand side, we have the support of inhomogeneity, and we have also the incident field, right? So generally, the incident field satisfies the Helmholtz equation in the entire space, except for some points or surfaces, okay? So say for Helmholtz functions, we'll have the incident field satisfying the Helmholtz equation everywhere. It's an entire solution to the Helmholtz equation, okay? So since I would like to see when this W is 0 in the exterior of perturbation, okay, so I'm actually going to consider not really the support of perturbation, which I denote here by O bar, but I would like to look at the unbounded component of the complement of the support, because the perturbation may be actually, we may not have perturbation inside these regions. So say the media may have voids, for example, right? So in my case, D is going to be the unbounded component of the complement of the support of the perturbation, okay? So now I have laid out mathematically everything to give me the answer to the question. So I would like to have this W equal to 0 in the complement of D, in the exterior. Okay, so that means that I'll have this equation. I write it in the next slide, but you can see it immediately here. So we have this equation in D, and W is identically 0 outside D. Okay, so if V happens to be a Helmholtz function, then W equal to 0 would mean that the far field operator evaluated at G would be 0. Okay, so now here it is. K is called a non-scattering wave number if there exists a non-trivial incident field. I define the incident field, again, I'm repeating myself, as such, satisfying Helmholtz equation, with scattered field satisfying this equation, okay, but being 0 in the exterior of D. So you can see that the system of the equation that would give me non-scattering wave number, actually it's overdetermined, because W equal to 0, say for Lipschitz boundary, means that on the boundary, we have prescribed the Cauchy data. So W equal to 0 on the boundary of delta of D, and we have also prescribed the Neumann data, okay, corresponding to this. So if A is identity, so if you have perturbation only in the lower order terms, then we'll have the both Cauchy data being 0, right? So you can see I minus A would be 0. So basically one has a Cauchy problem, okay, for this elliptic equation with the source involving the coefficient of the perturbation as well as the incident field. And the incident field actually is a solution to the Helmholtz equation in a region that contains the perturbation, right? So you see that we have a overdetermined problem. Okay, so now the transmission eigenvalue problem is actually trying to rescue, so to speak, this kind of overdetermined problem that we are not sure whether it has a solution or not, right? So we say that, well, how about I include in my system, I include also the equation of the incident field. So here I send the incident field V, right? But I say, well, no, I'm not sending the incident field V, but I'm saying that I'm looking for something that solves the Helmholtz equation. And because I have Cauchy data on the boundary, then I say, well, let me first forget about the incident field, the physical incident field that solves the Helmholtz equation also in the exterior of perturbation. So let me find a function that solves the Helmholtz equation also only in D. So then I have a beautiful system of PDEs. One is the equation for the incident field, but here now is part of the unknown in D. And then I have this equation for the scattered field. And then I have two boundary data. So two unknowns, two boundary data, it's perfectly fine. So we can actually rewrite this in terms of the total field. So if I rewrite this equation, for W plus V, then basically we have now two elliptic PDEs sharing the same Cauchy data. It's a beautiful problem, simply looking problem, okay? And it's an eigenvalue problem because I'm looking for K for which this V, which is part of the incident field, that is non-zero, and the corresponding U satisfy this homogeneous system. So it's an eigenvalue problem. Actually, interestingly enough, there is a paper by Levy in 1959. Actually, he posed this question, similar question, purely from the PD perspective. Okay, so basically, can two elliptic PDEs share the same Cauchy data? So if you see now the transmission eigenvalue problem, so the transmission eigenvalues contains the non-scattering wave numbers, right? So here where I summarize this discussion, I hope you followed the mathematical formulas there, but basically non-scattering wave numbers are subset of real transmission eigenvalue. Why I say real? Because this eigenvalue problem is non-self-adjoint. So now a real transmission eigenvalue is non-scattering wave number is this V part of the eigenfunction, okay, can be extended as a solution to the Helmholtz equation in the exterior of D, okay? So if it happens to be a Helmholtz function, then we are fine, actually. And then we have a particular physical incident wave, okay, that doesn't scatter at that wave number, right? But in general, theoretical sort of, but with sort of where the scattering problem makes sense, would be that the V part is extendable as a solution to the Helmholtz equation in the exterior of D. Okay, and here, okay, first item is basically the understanding of this non-self-adjoint eigenvalue problem. The second item is understanding when this extendability happens, when a transmission eigenvalue is non-scattering wave number. And this is exactly where the regularity of free boundaries. So you probably by now have gotten a sense that actually in the context of non-scattering, one has that the boundary of the inhomogeneity is like a free boundary, okay? It's invisible to outside, right? So here is where regularity of the free boundary comes in. So I'll briefly mention a bit later. Okay, so now another interesting thing is the following. So when I talked about the non-scattering wave number, I said V is what I sent. So V is the incident field. V is related to the scattering experiment, right? So the non-scattering wave number is associated with a particular experiment. Now the transmission eigenvalue problem, okay, doesn't pick up a specific incident field, right? So the transmission eigenvalues are inherent to the inhomogeneity, okay? So, and as you'll see later, actually, those transmission eigenvalues will help us to actually do some imaging of inhomogeneity, okay? So non-scattering related to a particular experiment, transmission eigenvalue problem is actually property of the inhomogeneity. All right, so now if you, when this problem was introduced by Kirsch and Colton-Monk, people started, what we do all the time with a new system of PDEs, one tries to separate variables for the configuration when it's possible. And this is possible for spherical symmetric. And by the way, actually, only for spherical symmetric media, you can get a meaningful sort of explicit solutions to this transmission eigenvalue problem or non-scattering. So for a square, for example, you can do, but it's very messy. Anyway, this is a configuration where you get a lot of insight. Okay, so if you separate variables, and I'm taking, of course, I cannot put an isotropic here because it breaks the spherical symmetry. Then one can show that there exist infinitely many real transmission eigenvalues. Under some assumptions, there exist infinitely many complex transmission eigenvalues. And it turns out that at a transmission eigenvalue for a sphere with a spherically symmetric coefficient, the eigenfunctions are indeed Hertz functions. So they are a superposition of plane waves. So there are also infinitely many non-scattering numbers, and where the far field operator is non-injective. In fact, all real transmission eigenvalues are indeed non-scattering wave numbers. And the incident field associated with those non-scattering wave numbers is precisely this corresponding V part of the eigenfunctions, okay? So I didn't dare to put all the work in this area, but actually there is, again, a substantial contribution from this audience in the inverse scattering for spherically symmetric inverse spectral problem for spherically symmetric situations. Natalia Tuskai and Sergey has done a lot of work in inverse spectral theory. And actually, this is the only configuration where people actually have solved the inverse spectral problem of recovering the, actually is the case for N. I think there are some works for both A and N that from a knowledge of the transmission eigenvalue. Anyway, so now this spherically symmetric configuration is unstable. And actually, I was asked many times how stable this is. So what happens if you perturb a little bit the spherical symmetric media? Do you still have non-scattering? And this was answered in a recent work of Fogelius and Shaw, where for special configurations, in the case when N is constant and A is identity, and they show that actually you lose the infiniteness of the non-scattering wave numbers, even if you perturb a little bit small perturbation, the circle with the constant N. And they actually are writing a follow-up paper where they're getting more general results for general coefficients. Anyway, all right. So now I have two problems. I have this transmission eigenvalue problem, and I have the when the eigenvalues are non-scattering wave numbers. So first, let me, because the transmission eigenvalue contain non-scattering wave numbers, okay, I would like to understand this more. And actually, even from practical point of view, transmission eigenvalue will turn out to be more important to inverse problem. Okay, so what is the state of the art of this problem? I have mentioned only the most sort of the work that actually has the state of the art result for various issues. So the discreteness Fredholm property of the resolvents and completeness of eigenfunctions together with asymptotics in the general case are provided in this work under some sort of ellipticity condition on the boundary. All right, so it's like equivalent to Egmont-Douglas-Nuremberg complementing condition, right? So then you'll see that if A is identity, this amounts to N being different from one on the boundary. So the location of transmission eigenvalues in the complex plane, Vodev actually has contributed a lot in this direction. And basically, he has shown that only for the case of A equal to identity, we have that the transmission eigenvalues lie in a strip. Otherwise, if A is not identity, the transmission eigenvalues have imaginary part that blows up. So there are transmission eigenvalues in the wedge around the imaginary axis. Why this is important? Because when we solve inverse scattering problem, the inhomogeneous transmission eigenvalue, so the resolvent of the transmission eigenvalue problem comes in, and the imaginary part of the eigenvalue blowing up causes a lot of problems. Okay, so here is the long-standing, very stubborn, open question in this area. And I'm formulating it. So basically, in general, is this condition necessary also for the discreteness of a transmission eigenvalue problem, right? So more explicitly, in a simpler configuration, okay? So suppose you have a identity, and then you have a boundary point where the inhomogeneity looks like this. Okay, so suppose that actually the background is the refractive index is n1, and in the inhomogeneity n2. So in what I was explaining, in my case, n1 was 1, but more generally, right? So now you have that the contrast is the difference between the refractive index in the inhomogeneity and the background. And suppose that in any neighborhood of such a point, you have a region that have the contrast positive and a region that has the contrast negative, okay? So if such a point on the boundary exists, okay, can you show the discreteness of the transmission eigenvalue, or maybe non-discreteness? So trying to understand the Fredholm property for such configuration, when the contrast changes sign up to the boundary that I call it, then can you say anything about the spectral properties of this media? So now for spherically symmetric case, I don't know how you can actually simulate this configuration, because then it loses, so to speak, the spherically symmetric configuration. But one possibility for people who has actually a lot of tools developed for spherically symmetric media, I'm throwing out this question. So you could probably have a case, say the refractive index changes like sine 1 over r minus 1. So say oscillate, and then you do it in such a way that oscillates 1 minus that refractive index oscillates between positive and negative up to the boundary. Okay, is it possible to show anything about the spectral properties of the media? Okay, so why this is important? This is important because actually in this paper, a beautiful connection between the discreteness of the spectrum of this problem and a big uniqueness theorem for the sound speed in photoacoustic imaging is made. So if it's possible actually to find necessary conditions for which the discreteness of this problem occur, transmission eigenvalue problem, then you actually can translate it to a uniqueness question for the sound speed. Otherwise, actually, you can see why this problem is complicated, because you can see that if you can reformulate the transmission eigenvalue problem as looking for the kernel of the difference of the Dirichlet to Neumann operators, one corresponding to one equation, the other corresponding to the other equation. So you can see here that the principal part of the difference of two Dirichlet to Neumann operator that roughly depends on n only on the boundary, okay, is not sign definite anymore if n1 minus n2 changes sign. So it's really very difficult problem. So now concerning the existence of real transmission eigenvalues, the recent state-of-the-art result actually is our old work in 2010, and only for that under those assumptions, it is known that real transmission eigenvalues exist, because the completeness of eigenfunctions and so on doesn't discriminate between are the eigenvalues real or complex, or so. Just say that if you have all eigenvalues, then the generalized eigenfunction form a complete set. So, but for non-scattering and then for using them in the inverse problem, one is interested in real transmission eigenvalues, because transmission eigenvalues are related to frequency, and hence the frequency is real. So basically, roughly speaking, the result is the following, that in general, if the contrast is one sign, not only on the boundary, but uniformly in the entire region D, then there exists an infinite set of real transmission eigenvalues. The assumption includes in it the assumption that actually we have real transmission eigenvalues if there is no absorption, no dispersion. Okay. And also one can prove monotonicity results in terms of D, A, and N, which is interesting because this is a non-self-adjoint eigenvalue problem. So somehow you don't have this Rayleigh quotient to actually get the monotonicity. Nevertheless, we use it as an auxiliary tool to prove some monotonicity. Okay, so now I open sort of what I'm going to say in the last 10 minutes. So if actually we can measure these transmission eigenvalues, and if we know that the media is absorbing, is non-absorbing nor dispersive, then actually those eigenvalues can tell us some information about the coefficient. All right, so now 2 minutes about. We have configuration where there are infinitely many real transmission eigenvalues. And in fact, actually, what matters is the sign of the contrast, not so much the regularity. So the coefficient can be as irregular as L infinity, and the boundary can be Lipschitz, okay? So now I get back to the question I started with. So now that we know that there exists real transmission eigenvalues, we know that for spherically symmetric media, all transmission eigenvalues are non-scattering. So in general, can we understand whether the transmission eigenvalues, real transmission eigenvalues, are non-scattering wave numbers? Okay, so I go back to the formulation of the non-scattering wave numbers, and you can see here that we have that. I rewrite it in an equivalent way. So I have that this equation for V is satisfied in a larger domain containing the inhomogeneity. This is the equation for W in D, and W is 0 in the exterior of D. Okay, so the fact that this equation is satisfied in the exterior of D makes actually this V real analytic function in omega. Okay, so you can see that actually it's understanding actually the boundary as a free boundary. So it's a free boundary, actually, the boundary of D if we have this non-scattering. So you can actually see it easier if I assume that A is identity. And if A is identity, then you can see here that you have the Laplacian of W equal to some source. And this source involves W actually also, but involves the N and involves the contrast, okay? And W is equal to 0, and the Neumann derivative is equal to 0. So this is exactly the classical free boundary problem that Caffarelli and his collaborators and many people in that community have studied. But here it's a little bit more complicated. Okay, of course, N will be like, we'll have to put some regularity on N, and V we have analytic, but the source term here involves W. So it's sort of the so-called obstacle problem with a sign changing source, right? So, but obviously the non-scattering configuration can be translated to a free boundary question. Okay, and we observed this in 2020, and this paper has appeared actually recently in 2023, and simultaneously Salo and Shangolian also has started studying this non-scattering configuration in a sequence of papers. Okay, so basically, as what people say in this free boundary regularity business, we can say about existence or non-existence of non-scattering wave numbers. So basically, actually, we say actually the results are about non-existence of non-scattering wave number. So basically, roughly, this result, there are a lot of equations here, says that if there is a boundary point, okay, where the coefficient are regular, say C infinity, and the contrast doesn't vanish at Z, okay, but the boundary locally near Z is not sufficiently regular, then we cannot have this hold. So we cannot have generally, we cannot have a non-scattering configuration hold. So it's a sequence of papers in this business. In inverse problems, actually, what is the relevance of this non-existence of non-scattering wave number? This is actually used in this paper to prove the uniqueness of the support of an inhomogeneity in the case when the support is a convex polygonal. And you use precisely the case that actually all wave numbers scatter. Okay, so I don't have time to introduce that new eigenvalue problem, but I would just want to mention briefly how can all this, what I discussed, be used in the context of inverse scattering theory? So the moral of the story I presented is that there exist transmission eigenvalues. The existence of non-scattering wave numbers is very is not a frequent occurrence, right? Actually, the only case we know that they exist is spherically symmetric media. So actually, this question of existence of non-scattering wave number is related to a lot of famous conjecture in this business, so I don't want to get to it. So only for spherically symmetric media, we know that they exist, right? So if we don't know that they exist, so it looks like always generically we can get response from any inhomogeneity, okay? If we probe by an incident field or by other more complicated incident fields than plane waves, right? So but we know that transmission eigenvalues exist for a larger set of inhomogeneities. It turns out that the link between the transmission eigenvalues and non-scattering wave numbers is made through this famous kind of analytic continuation result, or known as Runge type approximation, which says that if you have this V that is the eigenfunction corresponding to the equation of the background, then actually you can approximate it arbitrarily close by physical incident field, namely Herlot's wave functions or potentials and so on. So these connections make it possible to actually determine transmission eigenvalues from the scattering data. So if you have in your hands an approximation of the far field operator, then you can determine the transmission eigenvalues by solving this, by analyzing the so-called far field equation. So you look at the superposition of plane waves that resembles to the scattered field due to a point source. You cannot put zero here because the far field operator is compact, and it's hard to actually, it's very unstable to get sort of approximate zeros of the far field. It's just numerically unstable. But if you solve this equation briefly, okay, like linear sampling, I just want to mention sort of fundamental idea. Like when you do the linear sampling, you solve the regularized version of this. Or more rigorously, there is a generalized linear sampling question. If you look at a minimizing sequence of this functional, which is sort of a regularized far field equation with this term, and this term is like the norm of the Herglotz function, then it's possible to say that that if k is not a transmission eigenvalue, that this minimizing sequence make this go to 0, and this bounded, and if it's a transmission eigenvalue, then any sequence, minimizing sequence that makes this 0 has the lim sup infinity. So this is the way how we determine a real transmission eigenvalues. So these transmission eigenvalues now relates to the material properties, and you can use them to get information about the scattering inhomogeneity. Now, the limitation of the application of transmission eigenvalues to inverse scattering problem is because you can actually apply these ideas only for non-absorbing, non-dispersive media. Many materials are really have dispersion, and these exotic materials really their behavior depend on actually a particular dispersive relation. So you cannot actually use the transmission eigenvalue idea to get some information about material properties. I don't have much time, but do you think I can take a couple of minutes, like 4 or 5 minutes?
Yeah, please go on.
Okay, so I'm not going to get into details, but I'm just going to throw out an idea that we have developed actually to bring up other eigenvalue problems that sort of with respect to a modified far field operator or pre-processed scattering data play the same role as a transmission eigenvalue. And these new eigenvalue problems from the perspective of spectral theory bring up a lot of nice questions for some new eigenvalue problems. But from practical point of view, actually you can handle dispersive media, you can avoid multi-frequency data that you need to determine transmission eigenvalues and so on. Okay, so, and here is the idea, and I'll stop there. What you actually measure is the total field. And the total field is the physical incident field that you send plus the scattered field. So now you can say, how about I change the incident field, okay, mathematically, by augmenting it with using as an incident field the total field of something that I come up with. That would change the scattered field. That would make the inhomogeneity look like something else with respect to this mathematical incident field, okay, which I need to compute mathematically, right? And the total field is not going to change. So this mathematically in terms of the far field operators is the following, right? So suppose that you compute the far field operator corresponding to some artificial scatter, and you subtract it from the far field operator. And then you go through the same story I described today for 55 minutes and analyze when this modified far field operator is injective, okay? And if you do that, depending on the modification, depending on this sort of mathematical far field operator that you compute that doesn't involve the unknown inhomogeneity, then you come up with various eigenvalue problems. So one is the following. So the far field, the transmission eigenvalue has the issue that that you need this contrast to be one sign on the boundary. So you can change the contrast artificially by this mathematical trick, or you can use other parameters as eigenvalues instead of k. So this is my last slide. So if, for example, you compute the scattering due to some, say a big ball containing this unknown inhomogeneity, and you stick in here some parameters constant, a and lambda, right? Actually, you can do this explicitly or numerically if you don't consider a ball, right? And then after you look at you subtract the far field operator from the far field operator, physical, that you have from the scattering data. This means that you pre-process the scattering data. Then it turns out that the non-scattering wave numbers and transmission eigenvalues are replaced by sort of the eigenvalues of this problem, and potentially the extendability of V for the non-scattering. So now you have this eigenvalue problem. So now, if you still keep K as an eigenvalue, these parameters change the contrast. But you say, well, I'm going to fix K, and you can use lambda as an eigenvalue parameter. In this case, you may have actually complex eigenvalues, which you can determine because they don't depend on the physical frequency. So, and then you'll have a lot of flexibility. So this eigenvalue problem, so if you look at this eigenvalue problem as an eigenvalue for lambda, for example, it becomes like the kernel of the sum of two Dirichlet to Neumann operators. So it's easier handled and better behaved than the kernel of the difference, for example, right? So you have flexibility, and because you can determine those eigenvalues from the scattering data, then this has been used to get actually imaging of media, informations or density of small inhomogeneities and many more. And I don't have time, but some work that you could look at are these papers here and the references in them. And actually, I would like to mention one paper that is beautiful. Actually, is this paper, recent paper by Audibert, Chanel, Hadar, and this one, Audibert, Hadar, and Pourret, in inverse problems, where they use these modified eigenvalues to actually recover density of small inhomogeneities. Okay, so sorry for being out of time, and thank you for your attention.